Official members bounce, bust off the chrome. Realize it's real hell where we call home.
Official members bounce, bust off the chrome. Realize it's real hell where we call home.
From the heart inside one, I vision fat licks and mat clips. The chroma make the average imitator do backflips. You lack a pistol, so put a vest around the issue. Slugs will never miss you. Coming from members that's official.
Is that how you should build a real system?
Yes.
We laugh, but like that's actually what big database vendors do, right? There's some standard benchmarks like TPCC, TPCH, TPCDS. The queries are, the query's been around since 1992. You know what the schema is, so you say, okay, well, like if I know exactly what workload you're trying to test me on, I'll do some shortcuts to make things faster. So, for example, in TPCC, there's this table for the warehouse. Like think of it's like an Amazon fulfillment center. So there's a warehouse, there's a district, and then customers have orders, customers have items, right? So there's tree structure. But the number of warehouses is limited, and you never really update that table. So instead of defining a B+ tree when you call create index, you just say, all right, well, I know what table, this is a warehouse table for TPCC. I'll just make an array. Then you're jumping in exactly the right offset to find things, and it's super fast. Like an array where you know exactly the offset to jump into, it's way faster than a B+ tree. Right, that's 01. So they do tricks like that. So his question is like, is it okay to optimize your database system just for the workloads we're giving you? Yes, but in industry, you're not supposed to do that, but people still do it. All right. All right, let me make sure we're recording. All right, so a lot to cover, let's get started. So this is another good one, right? This is another key aspect of what we want to build in our database system to make sure, people can actually save their data and not lose anything. And it's why you don't want to write your own, database system. If you're building an application, you want to use an existing one because this is going to be hard. All right, again, for everyone in the class, Project 3 is due this Sunday. We have the Saturday office hours coming up on the 16th this Saturday, 3 to 5, same location and gates on the 5th floor. Project 4 has been posted last night, and that'll be due on December 8th, which I think is the week right before the finals. And then, again, the final exam will be due on December 13th. It will be at December 13th. I forget what the room is, but it'll be 8:30 a.m. Okay? Again, don't travel before this date. There won't be you can't come and take the exam early. Okay? All right, so last class was us wrapping up the discussion of concurrency control protocols. And in particular, we looked at multi-version concurrency control. And despite the name being concurrency control, the concept of maintaining multiple versions in a database system is going to affect the entire architecture. Right, we saw at the end of the case of indexes, your indexes kind of need to be aware, like, oh, I may be pointing at different versions of the same logical tuple or same logical tuple, and you have to account for that. And the execution engine has to be aware of these things. All parts of the system have to be aware of it. So for concurrency control, the protocols that we talked about are going to provide us with atomicity, consistency, and isolation guarantees, right, of the 4 things in ACID. And so the big thing that we've been dancing around or not really discussing, and I've mentioned it for a little bit, this is the red hat log will handle this, right? But the last piece of the puzzle we need for ACID is the D, durability. Now we're also going to rely on recovery protocols to give us atomicity as well, in case some transaction writes some stuff that, to a database and half it makes the disk and half doesn't make the disk, right? We need to handle that case as well. So it should be pretty obvious to anybody here why we want durability in our database, right? But the basic setup would be something like this, right? We have our transaction running T1, and when it calls begin, it starts reading A, and so that's not in our buffer pool, so we're just going to go out the disk and fetch that in, and put that in a frame. We talked about before, you guys built that in project 1. We know how to do that. That's fine. Now they go ahead and do a write on A, right? And that's no big deal. We just apply the change to the record or the object in a page in memory in our buffer pool, right? And then that's fine. And then now when they go ahead and commit, right, the guarantee or the property that we want to provide under ACID is that if we tell the outside world upon commit that your commit was successful, then no matter what happens to the database system, within reason, right, if it catches on fire and melts, like we still have to handle that, but we'll get that in a second. But if we tell the outside world that yes, your transaction is successfully committed, then no matter what happens, they should be able to come back and read that data. right? So let's say in this scenario here, we tell the outside world that your transaction is committed. The worst person in the world comes along, zaps the power station for the data center that's running your database system, and your buffer pool gets blown away because it's in memory, right? So now, of course, the problem in this case here, going back, this transaction modified A equals 2. We told the outside world that you committed, but we never put it actually on disk. So now when the system comes back, assuming we get power again, when we go fetch that page back in, we're going to get A equals 1. Again, under asset properties of durability, that should not happen. So today's class and next class will be about how to handle this situation. And this falls under the broad category of a description of recovery protocols for a database system. And again, it's going to provide us the consistency, durability, and atomicity guarantees we would need despite there being failures, right? So if transaction rolls back on their own, we got to make sure we clean that up. If the power gets pulled and we told the outside world transaction committed, we have to go clean that up. Now, it may be this in some case that a transaction goes ahead and commits, and we say it's committed, but we are about to send the message back to the client, to the application, and say, yes, your transaction committed. In that case, if the power goes down before that message gets sent, that transaction is still considered committed. Because depending on the recovery protocol we're going to use, changes will have made it to non-volatile storage. All right, so recovery algorithm is going to have two parts. There's the first part we're going to talk about today are all the extra things we're going to do while transactions are running so that we can handle the situation where there might be a failure. Right, so we'll do a little extra work while our transactions are running to make sure that we can always recover things later on. Next class will be dealing with the situation of, okay, after we've come back from a failure, like we got power back, the system comes back on, we have to look around at our disk and figure out, okay, what was the state of the system at the moment of the crash, and try to put us back into the correct state. So today's class is preparing for the failure. Next class is how to handle the failure. Okay? So the sort of overall outline is first we've got to discuss, obviously, what's going to happen in the buffer pool, right? Because that's where we have to stage all our changes in memory. So we have to understand what's going to happen, or what is the buffer pool allowed to do to prepare ourselves. And then we're going to talk about two different protocols, shadow paging and write-ahead logging. The spoiler is going to be write-ahead logging is an approach you're going to want to use, and most systems are going to use this. Shadow paging is what they invented at IBM back in the very first system, in System R. Some systems still do this today, but in practice, you don't want to do this. Write-ahead logging is always going to be the superior choice. Then we'll talk about what we're actually going to put in the write-ahead log, and then we'll do a preview of what checkpoints are going to look like, and I'll explain what that is as we go along. And then that'll segue into next class where we talk about how to do a better version of checkpoints and then load the checkpoints back in. And then we have a speaker today coming from Confluent, which is the big company backing building Kafka. Okay? All right, so as we talked about since the very beginning of the semester, this whole class has been about assuming we're dealing with disk-oriented database systems, where the primary storage location of the database is out on some kind of non-volatile storage, a disk, a spinning disk hard drive, an SSD, cloud storage, it doesn't matter. And then we obviously have to use the classic von Neumann architecture where we copy pages from disk into memory and operate on them in memory because that's going to be faster for us. And then there'll be some algorithms and choices we're going to make to allow us to maximize the amount of sequential access for reading and writing data from disk because that's going to be slower than random access. Whereas if it's in memory, we need random access very quickly. So if we got to modify something, we're going to first copy the pages into memory, perform the writes on the pages in memory, and then we got to write back these dirty records out the disk. Because again, if we crash, you're going to lose all the contents of DRAM. The research basically says you get 30 seconds of DRAM, you can actually still read things, but all your program counters, everything else is going to get blown away. So you definitely need to get things out on disk if you want to retain them. So the thing we have to guarantee is that, again, any transaction, for any transaction we told the outside world that you've successfully committed, we have to guarantee that their changes are durable, right? And of course, now that also means that we can't have any partial changes. Like if a transaction didn't complete, we don't want to retain half the write they made to disk, and because the other half was still sitting in memory, because then you would have torn updates, and that would violate the atomicity guarantee. So the two key primitives that we're going to rely on to achieve this are undo and redo. Right? And they're exactly as they sound, right? So the undo is going to be the process of removing changes of or effects of transactions that did not complete successfully, right? Because they aborted because the transaction said abort, or the system crashed, or the database system says, because of two-phase locking or OCC, they weren't allowed to commit, so you have to abort. It doesn't matter, the transaction is considered not committed. And then the redo process is just saying that, okay, for any transaction that did commit, again, where we told the outside world, at least attempted to tell the outside world that your transaction has committed, then we need to make sure that all of their changes are retained when we come back. Now, again, another transaction may overwrite those changes from from a previous transaction. That's fine, but we still need to make sure that every transaction that gets committed, everything's written out. So now, how we're going to actually do undo and redo is going to depend on what the buffer pool manager is going to do for us. So now we're going back to project one. We're actually going to modify it a little further because it needs to be a bit smarter about what's going on in the system to make sure that we can recover if there's a crash. So here's the basic idea. So say we have two transactions now. T1 wants to read A, write A, and transaction T2 wants to read B and write B. Right? So they're not conflicting. We're still going to run two-phase locking or OCC, whatever protocol you want on top of this. Right? These different layers are somewhat interchangeable. But for this transaction, they're commutative, so there's no conflicts there. So assume we have nothing in our buffer pool at the very beginning. T1 starts, does a read on A. So we know how to go at the disk, fetch that page where object A exists. Assume we have one page. Fetch it in our buffer pool. That's fine. Then we go ahead and do our write on A. All right. So then we update the record here, set it to A3. Now the context switch will come over here. We do a read on B. Well, that's already in our buffer pool, so that's fine. We're good there. Now we do a write on B. Again, it's in the same page where A was. We go ahead and update, and that's fine, and we're done. And then now, though, T2 wants to commit. So what do we say? Right? Any transaction where we tell the outside world that that it's committed, we got to make sure that its changes are written out to disk. Okay, well, what if I go ahead and write out this page here, write out the disk? What's the problem with this? T1 updated A, right? Those changes are in the same page where T2 modified B, and they went along for the ride because they're in the same page, because you can't do byte addressable updates. You got to do page-based, block-based. So this 4 kilobyte page with the change to A and B got written out when T2 committed. So now we tell the outside world T2 is committed. That's fine, so it's durable. But now we have the problem where T1 needs to roll back. All right? But now we got to go back on disk and undo the change we did on A. Right? So that sucks now, right? Because now we got to, if we just wrote everything out when this guy went to go to commit, it's going to get a bunch of stuff that maybe from transactions that haven't committed yet. So that's obviously bad. So the policies we've got to be aware of, there's two decisions we can make in our buffer pool manager. And the first one's going to be called the steal policy, and the second one's called the force policy. So in the steal policy, it determines whether the database system is allowed to evict a dirty object from the buffer pool, so a dirty page in our last example, that was modified by a transaction that has not committed yet. So even though T2 has modified it and they're going to commit, there's still another dirty change in there from T1. T1 has not committed. And the issue is going to be is that if we write out that dirty object to disk, assuming it's a page, then it's going to be overwriting on disk the most recent committed version of that object from another transaction. So with the steal policy enabled, you're allowed to evict dirty pages before a transaction is committed, and you essentially by the byproduct of that, you then overwrite the most recently committed version on disk. If you do no steal, then you're not allowed to do any eviction or overwriting, meaning every page in your buffer pool that has been modified by a transaction has to stay pinned in there. It cannot be evicted. So what we'll get to with the write-ahead logging is going to be using the steal policy, right? Because if we're allowed to evict things from uncommitted transactions, then that gives the buffer pool manager replacement policy, the LRUK piece you guys built, it gives it more options on how to, what frames it can free up. right? If you do no steal, then everything that a transaction modifies has to stay in memory. And of course, that means that if the transaction modifies more pages than you have memory for them, you're screwed because you can't evict anything out. The other policy is called the force policy, and this just says that when a transaction commits, is the data system required to write back and flush out all the changes for those dirty pages to the disk before we tell the outside world that your transaction has committed. So if you do the force policy enabled, the write back is required, meaning when a transaction calls commit, anything they modify in the buffer pool has to get written out. If you do no force, you don't require it. So forcing is going to make it easier for recovery because before I told the outside world you committed, all your changes are on disk. Fantastic. So when I crash and come back, I don't have to do anything. Right? Because I know if I told you committed, then everything's on disk and everything is correct. But of course, that's going to be slow now because now when I call commit, I got to flush everything. And if I've updated a billion tuples, that I got to wait for all those billion tuples to get flushed. So let's go back to the example we had before, but now we're going to do no steal force. So no steal says, again, that no dirty pages can be evicted from the buffer pool before a transaction commits. And force says when a transaction commits, then that's when we flush everything out. So again, we do the read on A, fetch that in the buffer pool, that's fine. We do the write on A, it updates the page, sets it to A3, that's fine. Then context switch it over to T2. T2 does a read on B, that's already buffer pool, we're good there. T2 does now the write on B and updates the page there. Now it wants to commit. So again, under the force policy, when we call commit, all the dirty pages that T2 modified have to be flushed to disk. But of course, we have the other problem with the conflict now is that under no steal, we're not allowed to write out any dirty pages from transactions that have not committed yet or any changes. And because, again, we're dealing, say, 4 kilobyte, 8 kilobyte pages, we have two tuples in there that got modified. One got modified by T2, one got modified by T1. Now we have this conflict where we want to flush this thing out, but we can't because part of the changes can't be flushed out. So a simple trick to fix this is just copy the page in a buffer pool, but only include the changes from the transaction that did commit. And then now we go ahead and write that out. So then now when we come back over here and T1 goes and tries to roll back, now this is trivial to do because there isn't any, none of it didn't modify nothing that it modified made it out to disk. So at this point we crash. We've already told T2 told the outside world T2 is committed, so that's fine. So we crash, come back. This thing is correct because it has changes from T2 but not T1. Do you think it's a good idea or a bad idea? Why is it bad?
It involves copy.
He says it involves a copy, the mem copy. Correct, yes. So this part sucks, right? Again, it's on PowerPoint. It's three cells in a page, whatever, nothing. I update 1 billion pages. I have 1 billion copies to remove anything, say in a highly concurrent system, you have thousands of transactions running at the same time. I got to keep track of what all pages they modified, which you're sort of doing anyway, but then now I got to make copies of them to figure out what's the bare minimum I need to have to write something out to disk. Right, so there's a lot of overhead involved in this. You don't want to do this. It does make, again, recovery easy, right? And it's pretty easy to implement, right? You never undo changes from aborted transactions upon recovery because nothing got written to disk, right? You don't have to redo changes either because on the force policy, you know that when you told the outside world a transaction is committed, all the changes are out on the disk. So when you come back, everything's just there, right? Like I said, but you still have to maintain the write sets about what the transaction changes they're making, and that you may run out of memory pretty quickly if you make a lot of changes. So again, no system will actually do this. A side comment I'll also say too is you actually burn out the hardware pretty quickly too. So on SSDs, they have actually a limited number of writes. So if you just write to the same cell over and over again, I mean, it's in the hundreds of thousands, but again, if you're flushing every transaction for every single page, you'll burn it out pretty quickly, right? So the way the hardware vendors get around this is you buy a 128 gigabyte SSD, there's really like 150 gigabytes on there, right? You just can't get to it all because they know the cells are going to burn out and they just replace it with ones that that have less wear leveling. But eventually you'll burn it out, right? No device is going to last forever. So again, if you're flushing 100,000 transactions a second, all the pages they modified on a single SSD, you'll burn through that pretty quickly. All right, so we want to be a little smarter about this, right, and not have to make entire copies every single time. So this is what shadow paging is. So shadow paging is going to be a no steal force buffer pool policy where instead of copying the entire database every single time, we're basically going to be doing what I just showed before. We're going to be copying pages, but we're not going to allow multiple transactions to update the same page at the same time. So now when I have to do a flush them out the disk, I don't have to excise out the parts from uncommitted transactions. Like I said, this is what IBM invented at System R in the very beginning. This is what a lot of the earlier database systems implemented in the 70s and 80s until write-ahead logging came around late 70s, early 80s, and everyone switched over to that. We'll see why this is going to have a bunch of problems other than the ones I've already talked about. So to keep it really simple, we're going to assume that we have there's only one writer transaction at a time, and then you can have multiple read transactions. So in some cases in SQL, you actually can call begin when you start a transaction. You can give a hint and say, I'm going to be read only. And the data systems can be aware of that and do some optimizations accordingly. So there's going to be essentially two page tables. And you think of that as the page directory of like pointing to here's the latest version or here's the page for this page number within this copy of the database. And so there'll be a master copy that's only going to contain changes from committed transactions. And then the shadow copy will be a temporary space where we'll apply the changes for uncommitted transactions. Then when a transaction goes ahead and commits, we flush out all those dirty pages from the shadow page table. And then we have this pointer that says, here's the current master page table. And we just swap that pointer, flush that out the disk, and now we're pointing to the old shadow becomes the current shadow becomes the new master. Right? So let's look at how those look. And this is basically how copy and write works. If you ever do like in Linux, like Linux is trying to do copy and write, it's basically the same idea. All right, so we have in memory, we have on disk, we have this master page table, right? And then when a transaction comes along, assuming that we're declaring that we're a read-write transaction, so we'll make a shadow page table, which is copying the current master page table, and all the pointers, think of like the mapping of a page ID to some page on disk, all the pointers are going to be exactly the same in the very beginning, because we're just going to point to the latest version of the database. But then now, if the transaction modifies a page, that the first time that it tries to modify a page, like page 1, we're going to make a copy of the page on disk in our buffer pool, write our change to that, and we do this for all the other changes. So we're just basically replacing the links in our page table to copies of pages for this particular transaction. Now, if any other transaction comes along that at this point and is read-only, then they'll look at the master pointer record, and they'll see, okay, here's the location of the master page table, and so it'll run all its transactions and read all the data it wants from the master page table. So it's seeing the older version of the database, doesn't see any of the changes that the writing transaction made. Then when the writing transaction goes to commit, right, we flush all any pages that it made, any changes it made in the shadow page table. Those get written out the disk. We then have to go update the master pointer record. Think of like it's in the header of the database file or some special location to say, okay, this transaction is committed, and now the master pointer is going to point to this page table, and this becomes the new master page table. Then again, any other transaction that comes along, say it's read only, they're gonna see these records. Of course, now we got to go ahead and clean up the old master page table. So it's just like sort of garbage collection we saw in MVCC, right? MVCC had multiple versions. You could have like for every transaction is updating the same record. You'll have a long version chain. This is basically a 2-version system. So then we got to go ahead and clean this up, reclaim the space, and then we'll just repeat the process the time the next transaction comes along. So what are some problems with this? Yes.
It wouldn't work very well with multiple transactions.
He said would not work very well with multiple transactions. Yeah, so the way you would have to, if you want to handle multiple transactions, you would basically have to run them in sequential order. I mean, actually, not really true. You could still do two-phase locking or OCC on top of this, and you could allow them to interleave each other, and you still protect protect tuples and records just as before. But when it goes time to commit, if I have two transactions in a batch that I run, one transaction finishes in 1 millisecond, the other transaction finishes in 1 second. The 1 millisecond transaction has to wait until the 1 second transaction finishes, then they go ahead and commit everything. So you basically run things in batches. The idea of having a single writer thread and multiple reader threads, that's not that outlandish. That's what how SQLite works, right? And it works pretty well. So recovery is super easy in this. Rollback is super easy as well. If a transaction aborts, what do? Just drop the shadow page table and just clean it up as if it was garbage like you would later on. And then when you crash and come back, it's super easy as well, because as long as this pointer got updated, then I know that the transaction is successfully committed. And so when I crash and come back, I ignore anything that's in the shadow page table, and the master page table has always the latest version of the database system, or of all the committed records. So undoing this is easy, because you just blow away the shadow pages and leave the master and the database root alone. And then there's no redo needed at all, because when you come back, everything's going to be there. Yes?
I'm just trying to understand this context within like the buffer pool manager context. So I understand that the master page table and shadow page table lives in like buffer pool manager,
Yes.
like, in memory.
Yes.
But like the actual pages that was being modified, like pointed by these page table pointers, do they bypass the buffer pool manager directly get through to this?
No, the question is like, what are these boxes and what are these arrows basically on disk, right? Yeah. So this is just the page table we had in your buffer pool manager before, but now you basically partition it and say like, here's the shadow pages and here's the master pages. And then you would do copy on write. So I'm showing the arrows happening like when, say it's going back here, when this guy modified 1, right? You would recognize, okay, well, I'm pointing to now a page in the master page table. So I'll make a copy of it in my buffer pool so I can make changes to it. And then at some point, I got to make sure I then write that out the disk as well. So in this case here, because it's a no steal flush, that when a transaction commits, that's when you write all the dirty changes out from the shadow page table out on the disk. For illustration purposes, I'm just showing it as they were happening. But that obviously would be slow. Okay, so we've covered a lot of these before, but why this sucks, right? So the copying the entire page table is expensive, right? And then the overhead of commit is high because you have to do that flush. You have to make sure that everything gets written out. Another big problem is that, and this is what the IBM people saw when they first built this, is that before all my data was nicely contiguous, again, thinking it out on disk. So going back here, before I made my shadow pages, everything was contiguous. So now if I want to do a sequential scan, I just read the pages one after another. But then after I've run a transaction and then I've cleaned things up, now I got empty space in here that now all my data isn't contiguous. So now I can't maximize the amount of sequential I/O I can do. So over time, things get fragmented, and you got to basically clean things up. You guys are probably too young for this, but in the old days of the hard drive, there used to be like a defrag command that you'd basically just repack everything, like almost like running vacuum full in Postgres. So you basically have to do the same thing here. So SQLite actually started off doing something a little bit like shadow paging, not exactly, but they had this thing called the rollback mode. The first versions of SQLite came with this, and then I think 2010 they then added the write-ahead log for performance reasons, obvious reasons, right? So the way SQLite's rollback mode would work is that you have your pages in memory, you have your database on disk, but then you have this other file on the side called the journal file. So that now when a transaction wants to modify a page, right, you bring it up from the disk, put it into your buffer pool, and then you immediately copy it out into the journal file before you made any changes to it. Then now you can go ahead and make your change in memory. Do the same thing for the next page here. Make a copy of it, write it out to the journal file. And then now, when the system crashes, say you say some of the changes got written out the disk for page 2, but then now if the system crashes before you write out page 3, at this point here, you know the transaction has not successfully committed. So the buffer pool in memory gets blown away, but then upon recovery, the very first thing you do is look for that journal file, and then you copy back the pages into memory, and because you know these are the original versions of the pages before a transaction that started modifying them made any changes. And then you just go ahead and just blindly copy them back out to disk to say, because you know this was the correct version of the database for these pages before whatever transaction was running made any changes. Right? And again, SQLite has a single writer thread, so they're not worried about a bunch of changes being made to pages by multiple transactions. They know that there's only one transaction could be modifying things, so either all their changes should get applied or none of their changes get applied. So then I think when a transaction commits, they just delete the file, mark the journal file as no longer needed. So then when you come back, you know not to reverse changes from a committed transaction. So another big problem with these approaches is that they're requiring the data system basically do a bunch of non-sequential writes to disk. Right? Remember we said that was one of the big design decisions we wanted to do in the beginning, was that we want to choose algorithms that may actually be not the most efficient way, but on pencil and paper, but because it'll maximize the amount of sequential I/O we can do, we'll get better performance. So that shadow paging stuff, or in the going back here, right, in my SQLite example, journal file, that's sequential I/O because I suck that into memory. That's fast, right? But I'm showing page 2 and page 3 being updated, but what are the updates to the pages are scattered around the file. Now I'm doing random I/O to go correct the database. And that's going to be bad. That sucks. So we want a way to convert random writes to disk into sequential writes, because that's always going to be much faster. And the way we're going to do this is through the write-ahead log. And as I said before, this is pretty much the approach that every data system that's out there today, they're going to be doing something like this. There might be some variance to what they're actually storing in the write-ahead log, when they actually flush, group commits. There's a bunch of tweaks you can do to this, but at a high level, this is what everyone's doing. So the idea now is that we're going to maintain a log file that's going to be separate from the heap files of the database, so where the tables are. And the log file is going to contain the bare minimum information you need to know what change a transaction made to an object in the database, and what was the state of that object before that change was applied. You can store some extra stuff in there, like checksums and timestamps and things like that. But the bare minimum you need is, here's the transaction that's making the change. Here's what they're changing. Here's what it was before. So I can do redo, or sorry, I can do undo. And here's what it should be after. So I can do redo. And the key thing we're going to have to do to make this all work is this part right here. Is that if we tell the outside world that a transaction is committed, then we need to guarantee that all the changes that it made to the database, the corresponding log records for those changes, are flushed to disk. And before we're allowed to write out any dirty page from the buffer pool out to disk, we need to make sure that the log records that made that page dirty, those are flushed out to disk first. So again, going back to think about I drew that diagram of here's all the levels, and then now we're adding recovery and current control, and it encompasses everything, because now our buffer pool manager needs to be aware of what transactions are, what changes they made, needs to know what log records are, because now when it runs its eviction policy, it has to know, okay, the log record for this that made this page dirty, that's safe on disk, I can go ahead and evict it, or this other page is dirty, its log record isn't on disk, I can't evict that. Because I would violate this guarantee and could cause us to lose data. So this approach is going to be using the steal no force buffer pool policy. So steal means we're allowed to evict pages from uncommitted transactions if those log records for that uncommitted transaction have been written to disk. And no force means that we don't require us to flush out all the dirty pages in our buffer pool when a transaction commits. We just have to make sure that the log records have been flushed out to disk. So if you sort of think of like the different choices now in the quad chart, right? The doing no steal force, like in shadow paging, that's trivial to do, right? But it's going to be sucked for performance. We want to be in this upper quadrant here. We want to be, we want steal to be turned on because we want to be able to evict things before transactions are committed. That gives us more flexibility and can make more room for data as we need. And then we want to be able to not require force because when a transaction commits, we don't want to flush everything out, which could be a bunch of random I/O. If we just flush out the log record, well, that's appending to a file. That's sequential I/O. We can make that fast and work well. So again, with force, it's going to require us to flush every page when a transaction commits, but it's going to get poor response time. With a no steal, we're going to get bad performance because we have to keep, we're keeping pages in memory that we could have been used for new data that we might need for other transactions. But it's really easy for aborted transactions because nothing got written to disk. And in this case here, no force would be great for us because, it's going to, if a transaction fails, the system crashes before things written out, we got to be able to redo the changes, and so we'll handle that with the write-ahead log. And then with steal, this allows us to flush out dirty pages even if a transaction that's updating it is still active, because we can reclaim that memory for other transactions that are running. So we want to try to hit this, again, the top quadrant here and the top right. So the way it's going to work is that there's going to be this log buffer space. It could be backed by the buffer pool, typically, not always, but it's some dedicated space in memory where we're going to stage all the changes from transactions for all the log records for those changes. And then we keep track of a way, we have a way to keep track of like a log sequence number, which we'll cover next class. We know the order in which these log records are getting applied, and then we know the log record number that corresponds to a change that was made to a page. So that when we decide whether to evict a page under the steal policy, we would know is the log record, what's the watermark, what's the threshold for the log record numbers that have been written to disk, and therefore I know anything that was modified by log records prior to that are durable in disk, and therefore I can evict it. And as we said before, a transaction is not considered committed. We don't tell the outside world that your transaction is safe and durable until we flush all the log records out to non-volatile storage. Now, the dirty secret is a bunch of systems actually don't do this by default, right? So everyone know what fsync is? Fsync is a blocking call telling the operating system that do not return to me until I know all my changes have been written or are safe on disk. And so in some systems, you call commit, and it'll come back and say, yep, good, you're committed. And then eventually, it actually get flushed out. So you can turn synchronous commit on, but you're obviously going to pay the penalty of that. And the performance penalty, we'll see how to make that faster in a second. But most systems, by default, don't give you, synchronous commits. It's like good enough. Like if you're okay with missing, maybe if there's a crash, you might miss the last 5 milliseconds. That might be okay for some people, some applications. All right, so the protocol is when a transaction starts, we're going to append a begin record to this log buffer we have in memory. Now, most systems, I'll show this for completeness and in the diagrams. In most systems, you may not even store the begin record until you see the first query of a transaction. So just because you call begin doesn't mean you actually start writing anything. In other systems, you don't actually put a begin at all because the first time you see a query, well, that's the beginning of a transaction. So that's the starting point. But for simplicity, we'll assume that there's always an explicit begin. And then now we're going to have a log entry, a log record for every single change we make to an object. And for this, we're going to store 4 things: transaction ID, the transaction that made the change, an object ID of what was modified by the transaction, and then the before value that we would need to do undo, and then the after value that we need to do redo. As I said, in different systems, we'll have additional information, maybe checksums, timestamps, and other information. We'll see we'll see different, actually the logging schemes. You actually can restore, like, here's the page number, here's the offset, here's the slot number. There's a bunch of extra stuff we can store in there, but for now, we won't put anything else. And then actually, as I said last class, the original version of Postgres really didn't do write-ahead logging because they were doing append-only MVCC, and they just assumed that the since I'm always making a new tuple, if I have a way to say whether a transaction is committed and write that out to the log, and then I don't need to go back and reapply any changes because I'm always doing copy on write. So if you're not doing append-only, if you're doing append-only MVCC, which most systems aren't, then you can get by without having to store to the undo, because you're always going to have the original version of the tuple. So then now when a transaction finishes, we're going to append this commit record to the log, and then before we tell the outside world that you're committed, we've got to flush the log up into that commit point, or maybe even a little bit farther, depending on how we batch things up. And then once that's durable on the disk, then we can acknowledge to the application, to the outside world, that your transaction is committed. So let's see what it looks like. So T1 starts, it wants to do write on A and write on B. So when it starts, calls begin. We add a begin entry to our log. Again, this makes it look like the write-ahead buffer log space in memory is much larger than the buffer pool. This is always going to be much larger, right? But for some, make it fit on PowerPoint, I'm just showing it approximate size, whatever. All right, so we call begin. So again, we add a begin entry to the write-ahead log. Then it does a write on A. So the very first thing we're going to do before we modify the page is we're going to put a log entry in with T1 of the transaction ID, the object we modified, and then the before and after value. Then we go ahead and modify the page. Because we actually want to record in the page, we'll see this next class, we'll record actually the log record number, the log sequence number of the change that we're making. So we need to put the entry in the log first, the buffer first, before we make the change. Now we do a write on B, same thing. I'm going to append the log entry in the buffer, go ahead and apply the change to the page. Then I go ahead and call commit. And then now at this point, assuming there's no other transactions running, I'll flush the log buffer and append it to the log file out on disk. And at this point, again, when we get acknowledgement from the hardware through the operating system, or if we're doing, if you're doing the direct IO yourself, like when we get the acknowledgement from the hardware that our changes have been flushed, then we can tell the outside world that our transaction is committed. Because now at this point, it doesn't matter whether this buffer pool actually, the dirty page actually makes that to the disk, right? If we now crash, all the contents of memory get blown away, everything we need to replay that transaction is out in that write-ahead log. We define the begin, we scan through and say, okay, well, the first thing you did was update A. All right, here's the value it should be. And then update B, here's what the value should be. So we can recreate the page that was modified by the transaction just through the write-ahead log. Is that clear? And now the benefit also too is, as I said, this is all sequential I/O, right? Because I'm just appending the log, writing out contiguous data out to disk. That's going to be way faster than if I updated a lot of pages and have to do a bunch of random I/O. Right? So now the committing the transaction is much faster. Furthermore, as you think about it too, like if I update 1 billion tuples and say there's 1 billion tuples across 1 billion different pages, right? If I got to flush all the buffer pool pages, I have to flush all 1 billion pages, which 1 billion times 48 kilobytes. Versus the log record, or have 1 billion entries, sure, but the amount of data I have to flush out is going to be much smaller than a bunch of 8 kilobyte writes. And that's all going to be sequential because it's all going to be contiguous memory. I just write all that out. Of course, now the problem is going to be if I'm flushing every single transaction when they call commit, that's going to be a bottleneck, right? Because the write time for SSDs, it's about a millisecond, 1 to 5 milliseconds. That sucks. If you have to go out to S3, forget about it. That's 100 to 300 milliseconds. So one trick we can do that was sort of similar to the example that I brought up when we were doing shadow paging or batching things up, we actually can batch together a bunch of transactions that have committed, right? They're all allowed to append to the log, and we don't have to worry about having a single writer thread. They can append in any order that they want, right? Because up above all this is going to be the concurrency protocol that's determining who's allowed to modify what data at what time. So all that still is in place. But then now I'll batch up their changes to the write-ahead log so that there'll be some timeout every 5 milliseconds or so. Then I'll say, okay, whatever's in the buffer now, that's going to get written out to disk. And so if you're the first transaction in that 5 millisecond window, yeah, you got to wait 5 milliseconds. But for some applications, that's not a lot of time. That's not a big deal. So basically, you have to maintain two write-ahead log buffers now. I'm not showing the buffer pool pages. I'm just showing the write-ahead log buffers. T1 starts, does a write on A, right? So we put an entry in the log buffer for that. Does a write on B, put another log entry on that. Then we context switch over to T2. We have to put the begin entry for that. Does a write on C, we have an entry. And then now, before we can do a write on D, the log buffer is full in memory. So we're going to go ahead and write that out the disk. We do that asynchronously, because no one's asked us to commit at this point, so it's not like we immediately have to do it. We'll write that out asynchronously, and then now we just tell any other transaction that wants to add new entries to this other log buffer and start filling that up while the other one's getting written out the disk. Then now say that there's a stall for whatever reason, right? Again, under the group commit policy, I would say, okay, every 5 milliseconds, every 10 milliseconds, usually something you can tune in the system. How often will it trigger a flush? So say these guys are waiting because they're going back to the client to get more information. It doesn't matter. So then at some later point, this say, okay, well, enough time has elapsed. I'll go ahead and write out this log buffer, even though it's not entirely full yet. And that's fine. Everything's still correct, right? And then now when this one gets flushed out, the other one is now free. The top one, so the transactions started pending log records there. Right, basically just doing double buffering here. Pretty good? All right, so if you go back to these sort of quadrants, the way to think about now a recovery policy or recovery protocol for a data system is how fast is it going to be at runtime and how fast is it going to be for at recovery time. Again, we're not really talking about the recovery process yet, but you can sort of see, we saw examples of this, like for shadow paging, recovery was instantaneous because you just ignore whatever's in the shadow page table when you come back. So for the runtime performance, the buffer pool manager with the write-ahead log approach is going to be the fastest under Steele or No Force because, again, I'm depending log entries. That's pretty easy to do, and I flush them out and write them out as I need. It's doing sequential I/O, whereas the shadow paging is going to be expensive because you're kind of blindly copying whole pages. But now for recovery time, shadow paging is going to be instantaneous because you don't have to do there's no log to look at. Whereas in with write-ahead logging, there is a log, and you basically have to replay that. Right? Because you have to do undo and redo to put the state of the database back to where it should have been at the moment of the crash. Whereas with shadow paging, there's nothing to do because the database magically or instantaneously comes back as being correct. All right, so now we've got to discuss what are we actually putting in the logs. I'm showing things on PowerPoint, transaction ID, object, before and after value, and it can be a bit more. So physical logging would be the approach of basically doing a byte level diff of here's what the page was before, and here's what it was afterwards. Or here's what the record was before, and here's what it is afterwards. Where you're actually specifying the exact physical location within a file, within a page, here's the changes that I made. Logical logging is going to be the sort of other end of the spectrum where instead of recording the low-level, byte-level changes I'm making to data, I just record, here's the query I executed to make that change. And then now when you basically recover after a crash, you just replay the query, re-execute it. Physiological logging is somewhere in the middle where it is going to be like physical logging where I'm going to keep track of here's the exact page that I modified by this transaction when I made a change, but I'm not going to tell you exactly what offset within that page I made the change. So I'll just record the slot number, and then now at runtime or when you recover the system, the data system is allowed to decide where in the page it's allowed to reapply the changes. All right. So again, say we do a simple transaction that has one query like this. If you're doing physical logging, again, you now within each entry for the updating the table, you're going to record like here's the page number and here's the offset within that page that I modified. And you're also going to record the changes you make to index pages. So you have to say for the primary key index, here's the modification I made to that page. Right? Because we had to make sure our indexes are in sync as well. Because it's basically another copy of the data. And we don't have to, because otherwise if you crash, come back, and all your indexes are gone, now you have to do a sequential scan to rebuild them. Logical logging just literally records, here's the exact query that I executed. So again, when you crash, assuming these things are in order, you're basically replaying the trace of the queries that were executed for transactions at runtime. This is more tricky to do. You typically only see this in in-memory systems where there isn't actually a table heap that you're maintaining. It's like you have snapshots of the database, and you bring them back, the entire thing back into memory, and then you reapply the changes. The tricky thing also too is like if you have non-determinism in the query, like I have where set val equals xyz, but if it was like where was val equals random or timestamp, I got to make sure that when I re-execute the query upon recovery, that I get the same, use the same seed or get the same value that I had when I ran before. So a little bit more work, you have to do for this. And then physiological logging, again, it's just a hybrid approach of this, where I'm still recording the changes I'm making within a page, but I'm just telling you here's the page number that I modified, or here's the index page that I modified. I don't know where the change is actually going to get applied. You'll figure that out. The system will figure that out upon recovery. So most systems are going to do physiological logging because it again provides you more flexibility upon recovery, more freedom when the system boots up of how to reapply the changes. So you don't have exactly the same physical layout within a single page, from one crash to the next, or one recovery pass to the next. You still have to make sure that you scope your changes in the same page, right? Because there's all these internal data structures to keep track of, like here's the page directory and so forth. You don't want to mess that up, but within the page you can reorganize things. And that indirection layer of the slot array gives us that ability. So a bunch of I've already said before, like logical logging is going to store way less data than physical logging and physiological logging. Like if that update query I showed before, if that updated 1 billion tuples, with physical logging and physiological logging, I need 1 billion entries for all those tuples that I modified. But with logical logging, I just store the query string. And that one query string could represent 1 billion changes. But like I said, if you start trying to recover the database after a crash, if you're just replaying the queries again, there's no magic button we can hit upon recovery to make those queries run faster than they would versus when they were actually running during regular execution. Like even though we're in recovery mode, we can't. The query takes an hour to run the first time. It's going to take an hour to run the second time in recovery. It gets even more trickier if you're not running transactions at lower isolation levels, because now you could if you start trying to intermix the transactions upon recovery, you may not guarantee the exact same outcome. You may read data that from another transaction that you didn't read the first time, but now you're reading the second time. So things get very, very difficult if you start doing this, and most systems don't do this for these reasons. So I'm going to show one quick slide about this other concept because I want you to be aware of it. But it's very common in the real world. But this is not something we'll cover in the exam. But remember at the beginning we talked about there's these OLTP databases, and you have these data warehouses, and you can stream updates from the OLTP database to the data warehouse and do all your analytics on that. And we talked about this being what's called extract, transform, and load. And the DBT guys came about this. That's sort of what DBT is providing for people, ability to do that. So what's cool about the write-ahead logging is that we can use the write-ahead log not just for recovery, but also for replication and propagation of changes from one database to another database. Because what is recovery? Well, it's taking the write-ahead log and looking at the changes I made and applying to a database. You could do the same thing for another database that has a copy of the data. We just sort of like it's in this virtual recovery mode. You have another database where you're getting all the changes, and you're just sending over the write-ahead log and applies it to that system. It's essentially how distributed systems do replication as well. So this is called change data capture, And you would use this in the context of an ETL or extraction from a load pipeline. So there's a bunch of different ways to do this. Write-ahead logging is the easiest one because you already have the mechanism to generate the write-ahead log for recovery. So now what you have is you just have to send that write-ahead log over to another system, who then applies the change and synchronizes its database with the original one. So you're piggybacking off a core component of the recovery protocol with write-ahead logging in a database system to do more things with it, to send changes. Because otherwise you have to replicate queries. Like it's another way to do this, and we'll see that later on. We'll talk about distributed databases next week. But this is pretty easy. So there's a bunch of tools that can do this. Oracle Golden Gate is probably one of the most famous ones. Debezium is an open source tool out of Red Hat. The reason why I'm kind of bringing this up now is today's talk, outside speaker, is from Kafka, and Debezium basically is the arrow piece that facilitates the movement of the write-ahead log from one system to another, and you would send that over Kafka, and Kafka guarantees that the data will arrive in order. Okay, so write-ahead log, that seems like the clear win. We want to do this, but there's an obvious downside, is that the write-ahead log is going to grow forever. Right? If I'm constantly running transactions, I'm going to keep appending things to the write-ahead log. They'll flush out the disk, that's fine, but this thing's going to grow indefinitely. And then now if I crash, come back, depending how long my write-ahead log is, that recovery time might be really, really long. Like if my system has been running for a year or 10 years, if I crash and come back, I don't want to have to replay 10 years of the log. So the way we're going to avoid this is periodically the system is going to take what are called checkpoints, where we're going to flush out all the dirty pages that are on disk, put a little hint in the write-ahead log to say at this point in time we did a checkpoint, and therefore the system may not have to go all the way back to the beginning of time in the write-ahead log to recover the database back to the correct state, because we flushed everything out. And then therefore, depending on what transactions are running, what they were doing, we could truncate the log and cut off at some point and not have to retain that long history. So I'm going to show a naive checkpointing scheme today, and how we incorporate this in the write-ahead log. We'll see why it has problems, and then next class we'll see how to actually do a more efficient one that everyone really does. So a naive checkpointing scheme would be blocking or consistent checkpoints, and basically every so often you're going to say, all right, I'm going to take a checkpoint, and you pause all transactions, pause all queries. Maybe if some queries start running, let it finish, right? You basically stop everything. Then you flush out the log records that are in memory to disk. Then you flush out all the dirty pages that are in the buffer pool out to disk. Write a checkpoint entry into the write-ahead log file, flush that, then unpause everyone. And again, because all the log records for any modified pages have been written to disk, even the transactions we haven't committed yet, which we're allowed to do under the steal policy, that when we crash come back, we have enough information to restore the database back to the correct state. So let's see how this works. So say we have this write-ahead log we're generating here, and then after this last entry by T3, we crash, right? So now when the system's going to come back up, it's going to look in the write-ahead log and say, aha, I took a checkpoint here at something. You basically start from the end, scan back until you find the checkpoint. So I know that at this checkpoint entry here, I got to look around, but before in going back in time and forward in time at that checkpoint to figure out what was running at this time, what changes did they made, and what transactions I need to guarantee those changes are durable on disk, and what transactions I need to roll back. So at this point here, we know, because if we look up in the log, we see, oh, T1 committed. When we took the checkpoint, we flushed all the dirty pages out the disk. Therefore, we don't need to do anything with T1. We can just ignore it because we know all its changes have been reflected in the pages on disk. So that's fine. That's good. But now for T1, for T2 and T3, we would look back and say, well, we see the begin entries for them before our checkpoint. So these were active transactions at the moment the checkpoint occurred, because we paused them and then took the checkpoint. So then now we've got to scan forward in the log and figure out whether they committed or not. So in the case of T2, we see a commit entry before we get to the end of the log, so therefore we know we told the outside world this transaction is committed, so therefore we need to make sure all of T2's changes made it to disk. But in case of T3, we didn't see a commit message for T3, so therefore we need to make sure that all its changes get reversed and undone. So the reason why we have to stall the transactions is because we don't want to start flushing dirty pages. And if a transaction, say, updates 2 pages, or one query updates 2 pages, we don't want to get half of the updates on one page and then get the updates on one page, write that to disk, and not write the ones from another one. All right? So we'll see how to fix this next class. The technique is basically called fuzzy checkpoints, where you allow transactions to keep modifying things while you're still running. And the way we have to handle this, we just sort of keep track of additional metadata about what was going on in the state of the system and what did our buffer pool look like at the moment we took the checkpoint. All right, and so then we have to do extra work. When we find the checkpoint, we scan back to figure out what transactions we're running, and then we scan forward to see whether they committed. But we'll see how we can add extra hints in the checkpoint records about what the actual transactions were, so we don't have to hunt forever to find them. Of course, now in our example here, it's on PowerPoint. It's a small number of log records, and then I put a checkpoint in there. But in a real system, we got to be aware of how often should I be taking a checkpoint? Because that can have real effects on performance, right? Just like the garbage collection stuff we talked about before, or the compaction stuff in log structure merge tree. Like if I run this background task of taking checkpoints over and over again constantly, then I'm going to be spending more time taking checkpoints instead of running queries and transactions, and it's going to make my system run slower. But if I turn off checkpoints or take a checkpoint every month, then now if I do crash and come back, now I got to replay 1 month's worth of logs. So there isn't a magic number I can say, oh, you take a checkpoint every 5 minutes, right? Even though that is often the default. It really depends on what is the acceptable amount of performance penalty you're willing to pay in your application, and how quickly you need to recover after a crash. And it varies, depends on what kind of application it is. I think I mentioned that there was this, the Puerto Rico power system or power company in the 1970s built a database system down there on the island. And because they were having such frequent power outages that were non-deterministic, they wanted a system that had instantaneous recovery. Because if they lost power, the system crashed. When it came back up, they didn't want to spend hours and hours recovering the database because it might crash, might lose power again. So they essentially did shadow paging because they were willing to pay the performance penalty at runtime, but that gave them the instant recovery they needed in their environment. So how often people want to take checkpoints and what their tolerance is for recovery times depends on what the application actually is. But honestly, most people run with the default. All right, so to finish up. So write-ahead logging is almost always going to be the best approach to handle loss of and crashes on the system when you have to write things out to non-volatile storage. And the way we're going to handle this is through the steal no force policy, where steal says, again, we're allowed to evict pages from transactions that have not committed yet out the disk, only if the log records that correspond to those changes that made that page dirty, as long as those have been flushed out the disk. And then no force says that we don't have to require all the dirty pages from a transaction be flushed out the disk when it goes and commits. So again, this is what we'll do at runtime. We'll append these log records to the buffer, and then occasionally take these checkpoints. And then upon recovery, we'll look in the write-ahead log, basically almost like the black box of an airplane, to figure out what was going on in the system at the moment of the crash, and then try to recreate the state of the database to be where it should have been. But through a combination of redoing transactions that did successfully commit and undoing the changes from transactions that did not commit. And the checkpoints allow us to sort of shortcut or jump more quickly into what should be the starting point for the database. Okay? So any questions about this? So the warning, so I would say next class we're going to talk about how to do better checkpoints and how to do recovery with Aries. And I would say this is probably the third hardest lecture of the semester, right? And rightfully so, because you don't want people to lose data. Getting this right is really, really hard. And so you'll see that we'll first describe the Aries recovery protocol, we're going to be very, very judicious and very careful. Like we're going to do this, 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 and this. And actually, in some cases, we'll actually be redoing changes that we didn't actually need to redo, because we want to be guaranteed that we're ending up the correct state. We're going to do this because people get mad when you lose data. Okay. All right. This is Mahesh. He's from Confluent, which I said is the company that is building Kafka and a bunch of other tools. And Mahesh can tell you, like I told you again, we use Kafka for change data capture and Debezium, but people use Kafka for a lot of things as well, beyond that. So the floor is yours, man. Go for it.
Okay, so thank you, Andy, Andy, and it's great to meet all of you, even though I can't see you. I'll just assume you're there. So I'm going to be talking today about some work that I've been doing at Confluent. So for those of you who don't know what Kafka is, give me one sec. Yeah. So Kafka is what you call a publish-subscribe system. Publish-subscribe is an idea that emerged from academic research in the 80s and early 90s. And it's just this idea that you have a bunch of people or machines who are producing data, producing a totally ordered stream of data, and you have other people or machines consuming that data. So you have a notion of a topic, you publish something to a topic, you subscribe to that topic, and you pull updates from it. And Kafka is something that got built maybe 10 to 15 years back. It was a project at LinkedIn. And then the founder of that project, Jake Reps, turned it into a company. So at this point, it's a pretty big deal practically. Confluent is a $1 billion revenue company. There are other companies that sell Kafka products that make quite a bit of money. But the thing about Kafka that's interesting is that it's not a cloud system. It was designed for on-premise workloads. So if you look at its design, it's basically a single machine, a broker, and then you run a whole bunch of these brokers, and the brokers do everything in one box, what is called a hyperconverged design. This is a great design if you're downloading and running Kafka in an on-premise setting. Not so great if you want to run it in the cloud. And today, a lot of the Kafka business is in the cloud. We're running Kafka as a service in the cloud. So when I came to Confluent 2 to 3 years back, the mandate was, can we build a cloud-first Kafka? What would that look like? And this turns out to intellectually not be that mystifying, right? Because Kafka, if you really think about it, topic is kind of like a file. There's something called a topic partition. I won't go into that. But it's basically like an append-only file. You're appending to the file. Other people are reading from it. And so the design of a cloud-first Kafka probably looks a lot like a distributed file system. You have a compute layer, you have a data layer, you need to store some metadata somewhere. And just to make it very clear, this metadata is essentially a map from a topic name, like a file name, to a list of data blobs that constitute the topic, right? So when you produce to the topic, you're essentially adding more pointers in this linked list. And when you're reading from the topic, you're just reading data from this list. All right. Hopefully that's crystal clear, you know what we're talking about. And so it turns out that if you really want to build a very scalable cloud-first implementation of the Kafka API, this publish subscribe API, then what you're really looking for is a metadata layer where you can store all of this metadata. So for example, when you produce data, when you publish data, you can write it to something like S3. And then you go to this metadata layer and you write a new pointer saying the next data blob in this topic happens to be at this location in S3. So someone reading the topic, subscribing to it, can go and read the data. Okay, and that is a bit rushed, so I apologize, but I'm trying to fit this into a 10-minute talk. So if building a cloud-first Kafka is all about the metadata, how do we make that work? So Confluent, like a lot of other companies, builds on top of cloud providers like AWS and Azure and so on. So the easiest thing we could have done is just take all of our stuff and shove it in a database like DynamoDB or something like that. I'm going to use the word database in a very loose, very imprecisely, you're taking a database class. So I'm not talking necessarily about SQL databases. I'm going to call DynamoDB a database. It has DB in the name. So the nice thing, I store all of my metadata in something like DynamoDB, is that from a very practical standpoint, it's a very easy system to operate, right? DynamoDB is not going to lose my data. So if the power goes off on my machines, I don't have to worry about durability. I kind of got the tailwind of what Andy was talking about, write-ahead logs and all of that. That stuff is really complex, and I don't want to deal with a lot of that. So DynamoDB takes care of it, right? The the problem is that if I store all my metadata in DynamoDB, it's extremely expensive because every time I want to read my data, I have to issue a request to DynamoDB. And these workloads tend to be fairly read intensive. The other issue is that, again, if I have a very chatty protocol, I have to keep going back and forth on give me the next entry in the linked list, give me the next entry, and so on. And there's a third issue, which is there's only like maybe 5 to 10 of these actually usable database APIs that AWS will give me, for example. So I have an impedance gap problem. The other option I have is I just build a new database from scratch and I run it on EC2, right? And then I can do anything I want. I can build, a spanner clone or whatever. The problem with that is I get all the properties I wanted, but it is extremely difficult to operate a durable database in production because as nodes fail, you have to make sure that you don't lose quorum, you don't have data loss, and so on. There's like a 10x, 100x difference between running a durable database versus just running some soft state servers. So the intellectual question we were looking at is, can we have our cake and eat it too? Can we somehow make the cloud responsible for durability? So all of our machines can reboot and lose power and lose state and it doesn't matter. At the same time, can we get the cost, latency, and flexibility benefits that we would like to have? And in a previous life, I used to work at Facebook before Confluent, before that as a professor, before that as at Microsoft Research. And when I was at Microsoft Research, I did some work with someone called Phil Bernstein, whom you would have encountered, I hope, in this class. And Phil had this idea that you could build a replicated database on top of a shared log. And then I did a bunch of work on making that a real system. So the idea here is fairly simple. If you give me any database, your favorite single node database, SQLite, MySQL, Postgres, or something simpler like RocksDB, BerkeleyDB, and so on, I can run multiple copies of that database, and I can keep these copies synchronized through a shared log. What's a shared log? It literally is a log that sits across the network from your database copies, and it's fault tolerant and it's replicated. Now, the implementation of the log itself can be some very complex distributed protocol. The important bit is we are separating the logic of the single node database from the logic used to replicate it. All right. Now, I'm going to brush through how this might work. So when a client talks to a copy of the database, it sends a command, a mutation, right? A SQL command to the database. The database does not execute the command. It appends it to the shared log. And then every copy of the database is playing that log forward and materializing the state. So the database is the log, right? Or the log is the database, as the famous saying goes. Now, why is this a good idea? Well, we kind of liked it because you can completely separate the database and the replication framework. So you can run any database with any API, and the logic used to replicate it doesn't change. And there were a whole bunch of reasons why in other settings, you got some properties from this architecture. You could replicate any API. You only needed one copy of the database. You didn't need quorums at the database layer. I'm not going to go into those in too much detail. But the one interesting property that, in the early 2010s, we kind of looked at it and we thought, well, that's nice, but we don't know why it's useful, is that you could use any consensus protocol under the log API. Once you have an API, you can have any implementation. You can virtualize and switch between implementations. And I remember in 2013, 2014, having a conversation with someone and saying, well, we could also just use something like S3 for the log, but why would we ever do that, right? That's such a dumb idea. And I kind of forgot about that idea for a while. Now, coming back to 2024 at Confluent, we needed this metadata database, and we wanted to somehow get the flexibility and the cost and latency benefits of having our own database, but we didn't want the headache of running a durable database. It turns out that the architecture I just described is a perfect fit because I can spin up some EC2 machines and I can run whatever database I want to. I can run RocksDB or something else. And I can implement a log directly on something like DynamoDB as a pass-through shim. and get a replicated fault-tolerant database, right, using the protocol I described. But every time I talk to a copy of my database, I'm synchronizing via this shared log. So this turns out to solve a lot of our problems because now we have, the cost benefits and latency benefits, because every time I want to read this database, I have a full coherent cache sitting on my EC2 machine. At the same time, if all my EC2 machines get blown away, my log is still in Dynamo. I'm missing some details because I do have to take snapshots and store it in S3, but but basically none of my EC2 machines have any hard state in this world. So I think that's pretty much all I have time for. I did want to make two statements that are kind of interesting. When I was a student, I did my PhD at Cornell, and I remember my professors would say things like, state machine replication, it's very important, it's used all over the place. And I really didn't believe them as like, it looks too simple and it looks too abstract. It can't be that important. I'm sure in industry they do something else. But it turns out that if you really spend enough time in the industry, you realize that all the big ideas are actually coming from academic research. They're coming from rooms like the one you're in, where someone has an idea and they write a paper and it turns out to be really impactful. And one of the reasons that's true is that when you come up with these new ideas, even though there's a lot of emphasis on saying, tell me why your idea is practical, often you can't tell at the time why it might be a good idea. So there's something to be said for just doing random research. And some of it may be good, some of it may be bad. That's fine. You just do a good job. And then over time, I think these ideas find practical utility. In my own case, the reason I got into these kind of databases was because, Phil came and gave a talk, Phil Bernstein, and he said, we can build a faster database. And I said, sure, I'll build you a log. And it turned out that at Facebook, the reason this architecture made sense was they needed simple databases that you could evolve over time. And the funny thing is that Confluent, the same design ends up being very important for saving cost, which I didn't anticipate, 10 to 15 years ago that would be the case. Thank you. That's all I had. Thank you.
All right, time for 1 or 2 questions. So the log he's talking about is basically what the whole class was about, right? Here's all the changes you're making to the database. And I was saying the CDC or the change data capture stuff, you don't have to replay the log on the same database that generated the entry. You can send it to whatever else. It doesn't have to even be the same database system. So I could take Postgres, take out the Red Hat log entries, send it over Kafka to whatever, and then replay it on MySQL, Mongo, whatever you want, or Snowflake. That's a very common pattern. The other thing I also point out too is he mentioned Phil Bernstein. Remember I talked about H.T. Kung, the guy who invented OCC, and how he left CMU to go fix Harvard. And I said the guy that invented a lot of this control stuff, that was a professor at Harvard, was a genius, and they didn't give him tenure. That's Phil Bernstein, right? The same dude, the guy that invented all this like transaction stuff. He's like almost 80, I think. But he's a genius. He invented a lot of this control stuff. He laid down all the core principles of how all this stuff works. That's the same guy that Mahesh is talking about. And he's still at Microsoft today. All right, any last questions?
I need something refreshing when I get finished manifesting. Too cold, a whole bowl like Smith & Wesson. One quart and my thoughts hip-hop related. Write a rhyme and my pen's intoxicated. Lyrics are quicker with a sip of more liquor. Since I'm a city slicker, brain waves are quicker. Rhymes I create, rotate at a rate too quick to duplicate. Feel a breeze as I skate. Mics at Fahrenheit when I hold it real tight. Then I'm in flight, then we ignite. Blood starts to boil, I heat up the party for you. Let my girl rub me and my mic down with oil. Record still turns with 3rd-degree burn for one man. I heat up your brain, give it a suntan. So just cool, let the temperature rise. To cool it off with St. Ides.